our course on hyperbolic systems. So at this moment it's not hyperbolic systems, it's a hyperbolic equation. Okay. So yesterday we talked about the characteristic method. Sorry. So remember, okay, characteristic method. Characteristic method. So we are looking for some function v of t, which is u. We did this yesterday, okay? Okay, so characteristic method doesn't mean always that we are looking for some constant function, okay? But in this case, we can have some constant function. Sometimes it's just to have some simple expression, simple control of the solution, okay? And we get that v prime of t equals to 0, and this is we get some. Remember, we did this yesterday, and it was prime is u of x of t. No, it's a. Now the equation is this one. So a is f prime, the derivative of the flux. And so here was a of u. Okay, and this is a constant. It means that it was a of u0 of x0, and we obtained that the characteristics are some straight lines. Okay, here maybe fine. Another one. I put maybe x01, x02. Okay, and the characteristic straight lines. Given by this is constant, and so x of t is equal to x0 plus time multiplied by a. Okay, and we see some question because we need to know what is u of x time, and this is u0 of x0 because u is a constant. Okay, so you fix time here, and you are your x maybe here. So this is the point x time, and you want to get some maybe expression, at least what is the solution. Okay, we assume that u. Okay, here we assume that u. Okay, we assume that u is C1. So here E0 is C1, so then u is C1. We can do this, can practice this derivatives, okay, in the strong sense. Okay. So the question, so how we can get, we know xt and x0 existence, maybe uniqueness. This is important question, because maybe x, there is no characteristic crossing this part, maybe all the characteristics avoid xt, so how you can calculate your solution. And another possibility is to have two characteristics, maybe going, imagine that two lines going in the same point. This is a problem because your solution will be u0 of x01 and at the same time u0 of x02. And the two values are different, so it's not a C1 solution. There is two values, so there is some discontinuity. We will see this problem. This is the main things. Okay, so there is a theorem who ensure the existence of such x0. Here you know x, you know time, but x0 is given by this implicit formula. Okay, so you have to solve this maybe generally by some Newton method or something like this fixed point method. Okay, to get x0. X is explicit. If you know x0, you are looking what are the x coming from here, it's okay. But when you know xt time and you are looking for x0, this is an inverse problem. So inverse problems generally are more complicated. Okay, so there's the theorem that if give you exactly when we can do the characteristic method. Okay, so if u0 is C1 function, okay, and we set d like the infimum of this quantity, derivative of this quantity of d maybe x0, okay, maybe, okay, I put it x, a of u0 of x. So in this problem, x is x0, okay? So the derivative of this expression with respect to x0, but there is only one variable, no problem. So in R, set, suppose finite number. So then the Cauchy problem, this one Cauchy problem, so it's u of x0. This is Cauchy problem. The Cauchy problem CP, like Cauchy problem, has a unique smooth solution. Sometimes you say classical solution, okay? In bracket or classical. But the word classical sometimes means other thing. Thank you, Joachim. Okay, I think everybody have seen these mistakes. Sorry. So classic solution, u in C1. So u has two variables. So r multiplied by 0 times some t star r. And what is fine is t star, we can compute it exactly. The maximal time is exactly optimal. So t star is equals to plus infinity if d is positive. It means that this function is increasing function, okay, or not decreasing if you want. Derivative positive, so your solution, you get some C1 solution, global solution on all the time, no problem, no discontinuities. Okay? But if d is negative, t star is equals exactly d is negative. So this is 1 and 2. T star is optimal, is a threshold value. So if you go just after T star, there is a problem, just after T star, okay? So the proof of one is not complicated, so I can give you this proof. And two, I will explain why it is. So I will set this function gt from R to R and x. Maybe I call it y. Okay, it's better. So it will be x0. Okay, y is gt of y So t fixed, okay, we fix time. And we set this function, it's not transpose, okay, it's just notation. But it means t is fixed, so I have only one variable function. So it's this one. So it's y instead of x0. So it's y plus t a of y, t multiplied by a of u of y. Okay. So, so gt is this function, okay? This is maybe here is gt, g time of x01, and this is maybe here. No, it's okay. So maybe you can. I have no place, but this is this point, you know, going from this, exactly this expression at time t, and so now you can do another one. Okay, put it here maybe. Okay. I do again. So this is y. Okay, this is the characteristic type t. So this point is gt of y, and this is t. Okay. So this is the direct sense from the characteristic. You go from the foot to get the characteristic in this way. But what we need is the inverse problem. We know x and we are looking for some y. So what is the derivative of this function? Prime. So the derivative is 1 here, plus t a, okay, d of dy if you want, a of u of y. Okay? So if d is positive, or 0, for this quantity, the derivative is positive. The infimum is positive, okay? So this term is positive, then gty prime is bigger than 1. Okay? Easy. Now, if d is a negative, so this quantity this is u, sorry, is bigger than, this is the infimum, so is bigger than d, then gt prime of y is bigger than 1 plus t times d. And if we take t here, for t less than t star, for this quantity is strictly bigger than 1 plus t star d. So strictly, so maybe, okay. And this is, maybe call it alpha. And alpha, I begin that this quantity, because t is less than t star, d is negative, okay? T is negative. And so this one is 0, because t star is minus 1 over d. Okay? So what happened here in both cases, so in both cases, you have the derivative prime is bigger than some constant. Maybe I call it alpha here also, which is strictly positive. So if you have this condition for any y, so exercise, if you have this property, the slope of any of the function is bigger than some threshold value which is strictly positive, then necessary this function is a bijection. It's a bijection. Exercise for a bachelor, maybe first year or second year. Okay, is a bijection. So we conclude that this is good for us because so we are needing here. So in our case, we need some to get this. We are looking for something like this. So if GT is a bijection, it means that X0 bijection from R to R. Okay. This is important. Okay. So if you have any X given in R, then there exists a unique X0. This is what we are. Depuis le début. OK. It's U0. U0. Ah, yes. Thank you, Joachim. My angel. Yes, this is U0. Sorry. Initial condition because here U0. U equals, we hope U equals to U0, but initial condition, we know U0. This is U0 everywhere. Sorry. And that's fine, I think. Thank you, Joachim. A good student. Better than the teacher. Okay, so then there exists a unique X0, which is maybe we can put it like GT minus 1. Okay, we have no explicit, we have explicit formula of GT, but what is the inverse? It depends on U0. Look, it depends on A, the flux. So if you take Berger's equation or traffic flow equation, A is not the same, and it depends also on the initial condition. Many dependence. So this is of X. Okay, and in this case, our solution is Ux of time. Okay, there exists a unique bit. We have, it's explicit, but okay, it's formal, but it exists. But to get it, it's maybe difficult. If you are looking for some zero of some polynomial, 3 degree, for example, I can prove that there is one solution such that the polynomial P of X equals to 0. But generally, you have the exact solution of X. You do maybe Newton method or something like this to get this. It's exactly the same. You know there is existence of the search. This is what we did. But the expression, explicit, except maybe which is simple is second degree. Okay, for third degree, fourth degree, we can have some almost explicit, but not so explicit. So the solution is something like is U0 of X0 at X0. Okay, is we can write it like this. Okay, see, okay, we get some beautiful explicit formula, but no, this is just to say, okay, we have U, which is, okay, function GT is continuous, is C1, etc. So of X. Thank you. This is X. That is dependence on time also, because if you change time, you change GT, not the same. Time is here, is included. Okay, this is, so this is for 1. And for 2, okay, for 2, maybe we will see that this is optimal time because something happens at this time. So if you, I just give you the idea. It's not complicated, but we have to reduce time is is important. So if you want that two characteristics comes to some point, this may be x1, x2 here. So imagine that you have some t, maybe t hat, some value, and t hat is x1 plus, no, sorry, t1 is the time, so here's some x maybe. Okay, so you have x1 is equals to something like x1 plus t, t over line, and a of u0 of x1, and x2 plus t, same x2. Is it possible? So if you put the equality between, then you get that t0 is something like, you put just equality, you have something like this. A u0, the x2, on a of u0 of x1 divided by x2 minus x1. Okay, so you can choose t star. Maybe if you take, this is close to, if x2 is, I put like this, okay, x2 is close to x1, this is close to the derivative d of dx of a of u0 of x1, okay? And you can take now, if t star between something like t star and t star plus epsilon, this is close to t star because this is infinite, this is close to -1 over d. And this is, okay, because the infimum is d, and you can get this close to, okay, so then, okay, this implies that, okay? So if we choose x1 such that this quantity is close to the infimum is not necessarily reached. But we have, if you put epsilon, you can say, okay, there is one point that we are between the minimum, the infimum, and the infimum plus epsilon, okay? So if we do this, then we get t star something, it's possible when t star is between t star and t star plus epsilon, okay? So this is why, so this is equality. If you have this kind of equality, then you have this equals to this, so they have some point, so there will be problem. So this is why it's optimal. Okay, you will have some discontinuity at this point. Okay. Now, I will give you some example, okay, the same example of traffic law. We try to calculate the solution by using the characteristic method. So maybe I will use this so let's see the traffic flow equation equal to 0. And okay, let's see, I will take maybe u0 of x0 is something like how we say 1/2, or 1/3, sorry, when x0 is negative. It's piecewise function. X0 plus 1/3. X0 is between 0 and 2/3. And 1 if x0 is bigger than 2/3. So this function is, okay, maybe I think there is a black one, yes. Okay, so this is 2/3. This is 0. So this is 1/3. And this is 1. Okay, so the theorem, we said if U0 is C1, this is not C1 function. So if you want C, this is C1, piecewise C1. If you want C1, we have to do something, some regularization, but it works. It's not a problem here. Okay, we see after that this is, it's not a problem. Okay, so we just, for calculation, it's better to use exactly this expression. It's better than we have something smooth here and here. Normally this is to respect the theorem, but the idea is fine, is okay. So what are the characteristics in this case? So just to see that, so f a of u 0, so f a of u is the derivative of this. Okay, this is 1 minus 2u. So a of u0 of x0 so it's one minus 2 u0 of x0. So here you will have 1 minus 2/3, it's 1/3. X0 is negative. I have to check. 1 minus 2, this quantity, so we get 1/3 minus 2 x0. This is if x0 is between 0 and 2/3. Okay, and 1 minus 2 multiplied by 1, it is minus 1 when x0 is bigger than 2/3. So what is the derivative of this? Here you have some constant. So 0, the derivative, when x0 is negative. The derivative of this, it's minus 2. Okay. We don't look what is in the, there is a problem of connection, but okay, there are two value derivative at the left and the right. This is not a problem. One is minus 0, the other is minus 2. This is 0 and 2/3, and the last one is 0. This is a constant. This function is like this one, okay, just 1 minus 2. So when x0 is bigger than 2/3. So what is T star here? What is T star? Is it infinity or something like -1/d? So this function is something like this. Okay. So what is d, capital D? The infimum of this function. It is yeah. That is 0 and -2. It's just a two-value function. So d is this one, the infimum of between 0 and -2. Okay, this is 0. This is slope -2. This one. So this is -1/d. So -1/d is -2. Oh, so T star is 1/2. So expect that in time 1/2 we will have some problem. Okay. So let's see what are the characteristics. How are the characteristics? Because I need this part. Be careful. Maybe I put it here. I think it's better if you let some place, because I will put some pictures here, and also, okay, just I will give the picture corresponding to the cars. So maybe this is 2/3. This is 2/3. This is 0. Okay. So the density here is 1. So the cars are 1s. 1 is mean that this. Okay. And the velocity is 1 minus u. So it's 0. Density is 1. The cars stop it here. They are stopping. But here, remember V is velocity is 1 minus u. Okay, so here is 0. Speed is 0. Yeah. Yes. But this is yes, but reality it has some centimeters. Yes, yes, normally. But if you want, okay, it's like yes. But if my picture will not beautiful, will not be beautiful if I do this. So yes, theoretically there are no space, but if you have to be careful with the car of the people in front of you, behind you. Especially if he is strong. Huh? Avoid problems, please. So here the density is increasing from 1 to 1/3. Maybe we will have something like this. Okay. And here I said 1/3. It means the equivalent of 3 parts like this. Maybe you have, so 1, 2, 3 here. other is here, here u equals to 1/3 and v, the speed is 2/3, okay? And here the speed v equals, this is v equals to 0, and v is between 2/3 and 0, okay? So here speed is 2/3, is a little bit less, and then 0, okay? That's fine. Okay, so let's see what happens. So what about characteristics? Characteristics. So remember, is x equals to x0 plus t a of u0 of x0. Okay. So x is equals to, you have to use this is a of u0 of x0 multiplied by time. Okay. Here. Okay. So normally we will get x0 plus 1/3 time if x0 is negative, and x0 plus a of, this is multiplied by time, so it's 1/3 between 0 and 2/3, and last one is x0 minus 1 minus t if x0 is bigger than 2/3. I try to do the picture of the characteristics. So we have x0. X0 is here, okay? And so the first, so remember that the function x is, okay, x in this way, okay? So you have to, so be careful. So 1/3, it means the slope is 3 in this picture, okay? So when x0 is negative, so maybe 3 is something like this, okay? So in the other sense, your x is here, t here is 1/3. It's not very strong, okay? But this is usually, I told you that we use this kind of picture, t in the y space. So don't be afraid with this. Say, oh, there is a mistake. It's not 1/3. This is almost 3. Yes, it's 3, but it corresponds to 1/3 for us, okay? So this is for x0 negative, all this part. Okay, x0 is negative. Maybe 2/3 is here. And the slope is -1. Okay. Sorry. It's 1/3 one. And between, you have different slopes, okay, and the characteristic. So what is this point? Normally this one is the connection, okay, if you take x0 equals to 0, okay, so you will get 1/30 is equals to, for this one, correspond as 0 for x0. So it's the same, but okay, this one. And x0 equals 2/3. minus t. Okay, you connect this line with this line. This is 0. So what do you get for t? What is t? 1/2. This is 1/2, exactly. So this is exactly the famous t star, 1/2. Okay? And okay, you can trust on me, the other lines are between, are something like this. There are some vertical line. So the vertical line means that x is equals to x0, and it means x0, this is 0. So it's 1/6. Okay? And also the other line will come here. Okay? So this is the maximum. We'll see what happened here. But first, let's see. Maybe let's take some time t strict less than 1/2, and to see what happened. Okay, calculation of the solution. Okay, so to get the solution, we need x0. So x0, because our solution is u of x. Okay, u of our solution is u0 of x0, but x0 depending on x and time by this relation. So x0, you have some x maybe here, there is 3 parts, okay? X here, x in this special area. Okay, this one is okay, and maybe x here. You want to see what is the, so this one characteristic is like this. Here is easy, but this part you have to see what is the characteristic. There is only one. For the moment, it's okay. So x0 is small calculation, but take time to write. And x0 is given by x time over 2t. And the other one, x0 is x plus time. So this is if x is 0 negative. Okay, but it means that if x is less than 1/3 time, because x0 negative means this one is negative. So this part, or this part. And the second one, when x0 is between 0 and 2/3, so this means that you can check x is between t/3 and 2/3 minus 3. And the last one is this part. Okay, so if x0 is bigger than 2/3, it means that x is bigger than 1/3 minus t. So, coming back to the picture. So next, what happened here is, sorry, and u of x time is given by, now is u0 of x0. And u0, this part, so here x0, u0 is 1/3, okay? u0 of x0 is 1/3. So it's 1/3 if x is less than 1 time. Second is x0 plus 1/3 in this case. and x0 is given by this, your place. So you will get something like x minus 1/3 time divided by 1 to t. This is if x is between 1/3 time and 2/3 minus t. And the last one is 1. So 1 in this case is when x is bigger than, sorry, 2/3, maybe it's 2/3 here. 2/3, sorry. Continuity is bigger than 2/3 minus t. Okay. So we'll get something. So these cars are arriving more and more, and they reduce the speed. Okay, so we'll get something like this. So this is this part, 1/3 of time. And the car arriving here, they will stop after. Okay, so this is maybe, this is first, but here it's 2/3 minus time. So this part is now here. Okay, and this is the solution for t between 0 and 1/2. Okay, so in the picture, next picture, so the 0 now, this one is a little bit here. Okay, Joachim told me I will do this. Okay, you have to solve the problem with the other drivers. Okay. So now, okay, they are stopping, and here also we reduce. But maybe so here the same. They are arriving. Okay, and this part where we reduce the speed is something like this. Okay, this is exactly what happened. And now we'll see what happened for time equals to 1/2. Okay, so when you arrive here, this is, look, t going to 1/2, you take the same formula. So this is 1/3 for x less than 1/6. And here, if you take t equals to 1/2, this is 1/6. And 2/3 minus 1/2 is equals to you can use your calculators. 1/6. So this region finish. That is 0. Okay, this point is equal to this point, and this region disappears, and this is for x bigger than 2/3 minus 1/6. So in this case, you will get exactly this behavior. So maybe here is 1/6, so at time equals 1/2, and you will get something like this. Some discontinuous function. this is for time equals to time is between 0 and third. So here exactly, okay, tac, 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 tac. But there are close, yeah? Yeah. This one. Yes, but I didn't respect the cars, the number of cars. Normally, yes, exactly. There is some conservation. Okay, so normally the cars arriving, okay, car arriving from this, okay. So we have to keep, because it's difficult to get exactly, these cars are arriving, and we have to keep that the number is the same. But this one is coming, maybe this one is coming from here. Yes, but this one. Good question. So this is just I put the time. This is 1/3 time. This is sorry. What is the other time? Is 2/3 minus t. Yes, normally. Yeah, yes, normally the same. Yeah. So here there are 3. I have to put 3. Yeah, yes, because the speed is 1/3. No, the density is 1/3. So the speed is 2/3. Well, I have to check. Okay. Maybe. Yeah. Yes. Compressed. This is. Okay. I have to check because this is 1/3 is the speed, is not the density. But the speed is 2/3. Okay. Okay. Anyway, maybe you have to check. Good question. So we arrive here, and then here you have 1/3. Okay, for the cars arriving, and the other are arriving. This is speed. So the density is 1. So the speed is 0. And here the density is 1/3. In my case, I choose this, and the speed is 2/3. Okay. So this is what happened at time equals to 1/2. So now we want to know what happens after this time. What do you think? This is what we will study. So until this time, okay, we did the characteristic because we have some continuous C1 functions, but from this time now we can't do the same derivative. So the solution is the strong sense. We can't do this. So we need some weak formulations to study what happened after. We are obliged. Okay. So we will see that, okay, that this kind, what will happen here is that all the cars have the same speed. They will arrive here, then they have to stop suddenly. Okay, hope there is no accident. They will arrive. This is called a shock wave. We'll see something. Okay, I have some videos. Maybe they need some help. Okay, I just show you something. Okay. Okay, this is okay. This is what we are studying. Okay, they're observing. Look, they're stopping. Up. Look, going left. And then when we start, we'll call this this is shock wave first, and when we start, this is called the rarefaction wave, and we will study this. Okay, and I have.
It's like when we all go to the snacks, okay, we go together and then It's increasing. Yeah.
So there's some experiments we are doing. Many people are participating in this experience. Explain how to look. You can find this in internet. Yeah, there is like this. It is circle. It's like one-dimensional case. Okay, they are beginning, starting. They just control the car in front of. Okay. So look sometimes up, shock waves and rarefaction when they start, etc. So they try to study this phenomena. And after they will show okay, what happened exactly, what we have seen. Okay. Oh, this is a shock wave. Doesn't mean accident, just okay, I will stop here for the video. And now so now I will use this part. If you want to, I can give you the link of this video. Just you have to put shockwave traffic flow and you get this. So now the characteristic method is not available. It's not okay to study what happened after, okay? So we need some weak formulation. This is what now it's weak solutions or weak solutions. This is a good example to see why you sometimes say, oh, why we are studying weak solution, etc. In this case, what happened after? We can do what is derivative. Okay, this is a problem. So we have to find something to study what happened after. And there is some phenomena. How to catch this phenomena? The strong formulation is not right. The strong derivative. So we need some weak formulation. So definition. If U is in an infinity of R by R plus to R is a weak solution of the Cauchy problem. CP is Cauchy problem. If we have some, for each test function, phi is, okay, we don't need necessarily C infinity, C1 is sufficient. I will explain what is this zero. So we have double integral of u plus f dx d time plus the integral to take account of the initial condition dx is equals to 0. Okay, so what is C01? Equals C1 functions with compact support. Okay, so phi, if you want, maybe this is the time x. I can do this maybe. This is the support of phi. It means that phi equals to 0 outside some bounded domain. Okay, compact support this. Okay, so this integral has signs. This is r multiplied by r plus here. Okay, this is to obtain this, you multiply the equation f of u and you do some integration by part. Okay, using some green formula. Okay, okay, but today we will concentrate on what the problem of discontinuities. So now we are interested in solutions. C1 piecewise. Okay, there are some discontinuity, but outside this, the solution is C1 smooth. Okay, like constant. So from this formulation, we get, it's not easy, but I can give you, at the end, it will give you some references. So if you assume that u is C1 piecewise, on R by R plus. So C1 U is a weak solution of the Cauchy problem if and only if satisfied something U is a classical solution. I explain what is classical solution of the Cauchy problem in each domain, where U is C1. Okay. If you are in some domain where U is C1, classical means you have to use the derivative in the strong sense. Because it's C1, you can use du over dt, du over dx. So you have to check this equals to 0. But through the discontinuities, we need some additional relation. U must satisfy the we call Rankine-Hugoniot jump relations that are in the form sigma by This is the jump of u is equals to the jump of the flux. So this is once is sigma multiplied by u left or u right minus u left. It's the same. Is equals f of u right minus f of u left. So imagine that you have some discontinuity curve like this. So what is sigma? Is the derivative, this is x of time, so sigma is x prime of t, okay? And imagine that you have some domain d1 and d2. So in some point here, you have some, your u is c1 here and c1 here. This is x and time, okay? And it's like a mountain near a beach. Sometimes you have some mountain like this, and then up you have like a wall near the beach. Oh, you can imagine this. This is gamma is the wall. Maybe it's not straight line because this is time. But if you fix the time, it means that you have something smooth here, and then up discontinuity, something like this. Not necessarily constant here, okay? But this discontinuity maybe moves with respect to time. And what is UR and UL? This is U left, okay, and this is UR because there is some discontinuity, so you have the limit at the right and at the left are not the same. So UL is the limit of U at the discontinuity, I say. So left it's minus epsilon and time when epsilon going to 0, okay? And U right, the same limit, but plus epsilon time when epsilon is going to 0, okay? Epsilon positive, okay? This is what is here, the discontinuity, the values, it's like here. Here U left is 1/3 and U right is 1, okay? So this is the theorem give you, this is the general formulation, but in our case, we are interested in this kind of solutions. So we have just to check this, okay? For the shock. J'ai pas encore parlé de... Ouais, mais j'ai pas encore... Okay, so now I just... So let's example. Okay, with f of u for traffic lights, and let's take this this problem. Okay. So u0 is okay. Instead of 0, this is the time was one half, but we can shift the time to 0. Okay, the same problem. So u0 is I say this is 1 and 1/3. Okay. This is 1/3 and 1. Imagine this is at 0. Okay, to simplify. At time equals to 0 and x equals to not 1.16 is 0. Okay, just translate. Okay, this is my u0. And I will show you that the solution we have seen, maybe with the water, is a weak solution, satisfy this. So I will take, the solution is 1/3. Okay, and if x is less than some sigma t and 1, So we have some, this function, the discontinuity is something like this. Okay, and so sigma, what is sigma? Okay, this is 1/3, this is 1. So sigma has to satisfy this equation. Okay, so sigma, what is the speed? The speed, when you see the front going back, it has some speed. The speed we can calculate explicitly. So the speed is f of, so this is your left and this is your right. Okay, and it's a constant. U0 is a function, is constant here, is 1/3, and here. So f of 1 f of 1/3 divided. So f of 1 is 0. Okay. F of 1/3 is 1/3 by 2/3, so it's 2/9, and 1 minus it's 2/3. So look, it's minus 1/3. So it's negative. Okay. So this solution will go back. The speed sigma. So in this, yes, sigma is negative. Okay. So sigma is, maybe my picture is not correct, but okay. Anyway, so sigma is negative this way. I will change. So this is 1/3. This is UR. Okay, so if you take any time here, look, 1/3 will in this part and 1 from here. So this is going back. Okay, so let check. Yes, Joachim told me about something which is important. So if you see the characteristics, so the characteristics here is okay, A of u is 1 minus 2u. So the characteristic in this case, 1 minus 2/3 is 1/3, and in this case is minus 1. Okay, so the characteristic are going like this. And the other is minus 1 is going like this. Okay, this is the characteristic. Because this part is constant, you can calculate the characteristic, but there is some strong thing. Okay, so the characteristics are going, we say, are going to the shock. This is important because we can have some discontinuity where our characteristics are going away from the shock, and this shock is not physical. This one is physical. This is very important. All the informations here are going to this line. So this part we can do characteristic, this part also, but there is some strong line here. So we represent the shock like this, okay? So other things, so I said, we have to check this. This is okay, we have some discontinuity. Our solution satisfy, okay, this, and we have chosen sigma such that we have to. Now what about 1? 1 say, where u is C1, we have to check the solution. But, okay, so this is 2. So here is 1/3. So if you take this, we have 2. And 1 it means where u is a constant, or this part, x is less than sigma t, this domain, this is D1, this is D2, this is u is C1, u is constant, it's C infinity. So we have to check that u satisfies this equation. What is the equation? In D1 and D2, you have plus d of dx of f of u equals to 0 exactly, because u is constant, so you differentiate 1/3 by time is 0 plus this is constant, 1/3 multiplied by this, the differential is 0, 0 plus 0 gives 0. So you have you satisfied this equation in this junctions. This is what is written here. Classical strong sense of the derivative. Okay? And also in this second domain is also constant here. So no problem, constant, satisfy necessarily this kind of equation. So we have 1 and 2. So this solution, this function is a weak solution of our problem. And this is what we have seen, exactly. So U is a weak solution of the Cauchy problem. Okay? Okay, I will give you another, I have until half, yeah? 30, okay. So now I give you another example. Example 2. Traffic lights. Okay, Prof told me this, but be careful with this. So now is, yeah, we are close to the traffic lights. Traffic light is red. Everybody stop. So the initial condition is U0 of x is 1 when x is negative and 0 when x is positive. Well, this situation. So what happened after? Now the light green. What happened in this case? Okay, the light is green. So usually the cars are starting. But imagine that the first driver, like Gerald this morning, has a problem with his car. Okay, so nobody start. But okay, it's a real solution. So let's take this solution. If we take u of x time the same, 1, we will see that this is also a weak solution of our problem. Okay, this problem, the first driver doesn't move. So let's see. So we are, in this case, what is sigma? Sigma is f of u left minus f of ur divided by ul minus ur. So f of 1 is minus f of 0 divided by 1 minus 0. F of 1 is 0. Okay, this is a 0. Sigma, the discontinuity doesn't move. Discontinuity, this part here doesn't move. This is the discontinuity. Okay, so, and in D1, so our domain, this is the discontinuity. Dt with sigma equals to 0. Okay, and this D1u is 1 and 0. Okay, so 2. Okay, because sigma is 0. Here is 0. This is 0 multiplied by time, if you want. So it works like before. And for 1, so u is a constant. In D1, maybe u equals to 1, so it's okay. 1, satisfy this. It's a constant. And also in D2, u equals to 2. That's okay. So this is a weak solution of our problem. is a weak solution of our problem. Okay, so tomorrow I will give you another solution, which is maybe more commonly used, is that the cars will start. Okay, so I give you the expression of this solution, and you can check if everything is okay. Imagine that the first driver is I can give you maybe three solutions. So solution 2, maybe this is U1, A, and B. So imagine that the cars, okay, the cars, they move at some special form, okay, all moving at the same speed, okay. So we get some, this is discontinuity 1, say gamma 1, this is gamma 2. So maybe here is U is 1, maybe here U is 1/2, and here U is 0. So they are starting like a military parade. Military parade, every car, in the roads you don't drive like this. But in a military parade you have this kind of movement, okay? So in this case, so this front will go back. We'll have some discontinuity here. So you will get some, and same thing, this one is going in this way. So here U is equals to 1. So you have to calculate sigma 1, sigma 2. What is sigma 2? What is the speed of this discontinuity and also the speed of discontinuity? You use the Rankine-Hugoniot relation and you have what is the speed, okay? And U here is 1/2 and U here is 0, this part, okay? So in this domain, U is classical solution, is a constant. Derivate satisfies this equation. In this domain, D2, it's okay. In this domain, it's okay. So now what is happened through the discontinuity? So this part, you have just to calculate sigma. You don't take any sigma 1 and sigma 2, and you have some solution. So U of x time is equals to 1 if x is less than some sigma 1 t. It's easy to calculate it. And 1/2 if x between sigma 1 t and sigma 2 t, and 0 if x is greater than sigma 2. So this is okay. You sigma 1 equals something and sigma 2 equals something, then you have 2, okay, and 1, okay, in D1, D2, D3, there is 3 domains. This is D1, because U is constant. And then U, this one, is also a weak solution of the problem, of the Cauchy problem. It's another one. And also this one is special, it's a military parade. And I will give you what is the good one, what we call the physical one. So this is just to show you that we will have some problem that the weak solution is not unique. We have problem of uniqueness. So we have to select what is the good solution. So check for tomorrow this, and I will give you what is the right solution. So the right solution is that the cars are starting slowly, and the first one is going faster than the second one, and the third faster than because the first one is free, nobody is in front of. But the second one, he has the first driver in front, so I have to be careful. Okay, so I will give you this third solution, and this is we say the physical solution. Okay, it's called the rarefaction wave. We have seen in the movie that the cars are starting maybe faster and faster. Okay, so it's not a constant like this. This is the speed here is v equals to 1 minus u, so it's 1/2. Everybody is moving at the same speed, except military parade. In reality, we have noticed. Okay, we'll see this tomorrow, and we continue maybe after we'll see what is this good selection of the weak solution, because there is no uniqueness. We can see here because we have 2 solutions, and we'll see after maybe a part of what happened for systems. Thank you very much.